Hello friends, in our previous discussion we learnt that a substance that has a fixed chemical composition throughout is called a pure substance. Then we learnt that in the liquid phase a substance that is not about to vaporize is called a compressed or subcooled liquid. In the gas phase, a substance that is not about to condense is called a superheated vapor. During a phase change process, the temperature and pressure of a pure substance are dependent properties. In today's discussion, we shall be talking about property diagrams for phase change processes. The TV diagram. The phase change process of water at 1 atmosphere pressure was described in detail in last lecture and plotted on a TV diagram. Now we repeat this process at different pressures to develop the TV diagram. Let us add weights on top of the piston until the pressure inside the cylinder reaches 1 megapascal. At this pressure, water has a somewhat smaller specific volume than it does at 1 atmosphere pressure. As heat is transferred to the water at this new pressure, the process follows a path that looks very much like the process path at 1 atmosphere pressure as shown here, but there are some noticeable differences. First, water starts boiling at much higher temperature at this pressure. Second, the specific volume of the saturated liquid is larger and the specific volume of the saturated vapor is smaller than the corresponding values at 1 atmosphere pressure. That is, the horizontal line that connects the saturated liquid and saturated vapor state is much shorter. As the pressure is increased further, this saturation line continues to shrink and it becomes a point when the pressure reaches 22.06 megapascal for the case of water. This point is called the critical point and it is defined as the point at which the saturated liquid and saturated vapor states are identical. The temperature, pressure and specific volume of a substance at the critical point are called respectively the critical temperature TCR, critical pressure PCR and critical specific volume VCR. For helium they are like this: T critical is equal to minus 267.85 degree centigrade, P critical is equal to 0.23 megapascal and V critical is equal to 0.01444 meter cube per kg. At pressures above the critical pressure, there is not a distinct phase change process. Instead, the specific volume of the substance continually increases and at all times there is only one phase present. Eventually, it resembles a vapor, but we can never tell when the change has occurred. Above the critical state, there is no line that separates the compressed liquid region and the superheated vapor region. However, it is customary to refer to the substance as superheated vapor at temperatures above the critical temperature and as compressed liquid at temperatures below the critical temperature. The saturated liquid state in the TV diagram can be connected by a line called the saturated liquid line, and saturated vapor states in the same figure can be connected by another line called the superheated vapor line. These two lines meet at the critical point, forming a dome as shown in this figure. All the compressed liquid states are located in the region to the left of the saturated liquid line called the compressed liquid region. All the superheated vapor states are located to the right of the saturated vapor line called the superheated vapor region. In these two regions, the substance exists in a single phase, a liquid or a vapor. All the states that involve both phases in equilibrium are located under the dome called the saturated liquid vapor mixture region or the wet region. The PV diagram. The general shape of the PV diagram of a pure substance is very much like the TV diagram, but the T is equal to constant line on this diagram have a downward trend. Consider again a piston cylinder device that contains liquid water at 1 megapascal and 150 degree centigrade. Water at this state exists as a compressed liquid. Now the weights on the top of the piston are removed one by one so that the pressure inside the cylinder decreases gradually. The water is allowed to exchange heat with the surroundings so its temperature remains constant. As the pressure decreases, the volume of the water increases slightly. When the pressure reaches the saturation pressure value at the specified temperature, the water starts to boil. During this vaporization process, both the temperature and the pressure remain constant, but the specific volume increases. Once the last drop of liquid is vaporized, further reduction in pressure results in a further increase in specific volume. Notice that during the phase change process, we did not remove any weights. Doing so would cause the pressure and therefore the temperature to drop, and the process would no longer be isothermal. When the process is repeated for other temperatures, similar paths are obtained for the phase change processes. Connecting the saturated liquid and the saturated vapor states by a curve, we obtain the PV diagram of a pure substance. Extending the diagrams to include the solid phase. The two equilibrium diagrams developed so far represent the equilibrium states involving the liquid and the vapor phases only. However, these diagrams can easily be extended to include the solid phase as well as the solid liquid and the solid vapor saturation regions. The basic principle discussed in conjunction with the liquid vapor phase change process apply equally to the solid liquid and solid vapor phase change processes. Most substances contract during a solidification, that is freezing process. Others like water expand as they freeze. These two diagrams differ only in the solid liquid saturation region. The TV diagrams look very much like the PV diagrams, especially for substances that contract on freezing. The fact that water expands upon freezing has vital consequences in nature. If water contracted on freezing, as most other substances do, the ice formed would be heavier than the liquid water and it would settle to the bottom of rivers, lakes, and oceans instead of floating at the top. The sun's rays would never reach these ice layers, and the bottom of many rivers, lakes, and oceans would be covered with ice at times, seriously disrupting marine life. We are familiar with two phases being in equilibrium, but under some conditions, all three phases of pure substances coexist in equilibrium. On a PV or TV diagrams, these triple phase states form a line called the triple line. The states on the triple line of a substance have the same pressure and temperature but different specific volumes. The triple line appears as a point on the PT diagram and therefore is often called the triple point. The triple point temperatures and pressures of various substances are given in this table. For water, the triple point temperature and pressure are 0.01 degree centigrade and 0.6117 kilopascal respectively. That is, all three phases of water coexist in equilibrium only if the temperature and pressure have precisely these values. No substance can exist in the liquid phase in stable equilibrium at pressures below the triple point pressure. The same can be said for temperature for substances that contract on freezing. However, substances at high pressures can exist in the liquid phase at temperatures below the triple point temperature. For example, water cannot exist in liquid form in equilibrium at atmospheric pressure at temperatures below 0 degree centigrade, but it can exist as a liquid at minus 20 degree centigrade at 200 megapascal pressure. Also, ice exists at 7 different solid phases at pressures above 100 megapascal. There are two ways a substance can pass from the liquid to vapor phase. Either it melts first into a liquid and subsequently evaporates, or it evaporates directly without melting first. The latter occurs at pressures below the triple point value, since a pure substance cannot exist in the liquid phase at those pressures. Passing from the solid phase directly into the vapor phase is called sublimation. For substances that have a triple point pressure above the atmospheric pressure, such as solid carbon dioxide, that is dry ice, sublimation is the only way to change from the solid to vapor phase at atmospheric conditions. The PT diagram. Figure here shows the PT diagram of a pure substance. This diagram is often called the phase diagram since all three phases are separated from each other by three lines. The sublimation line separates the solid and vapor regions. The vaporization line separates the liquid and vapor regions, and the melting or fusion line separates the solid and liquid regions. These three lines meet at the triple point where all three phases coexist in equilibrium. The vaporization line ends at the critical point because no distinction can be made between liquid and vapor phases above the critical point. Substances that expand and contract on freezing differ only in the melting line on the PT diagram. The PVT surface. The state of a simple compressible substance is fixed by any two independent intensive properties. Once the two appropriate properties are fixed, all the other properties become dependent properties. Remembering that any equation with two independent variables in the form z is equal to z x y represents a surface in space, we can represent the PVT behavior of a substance as a surface in space. Here t and v may be viewed as the independent variables, that is the base, and p as the dependent variable, that is the height. All the points on the surface represent equilibrium states. All states along the path of a quasi-equilibrium process lie on the PVT surface, since such a process must pass through equilibrium states. The single phase region appears as a curved surface on the PVT surface. and the two phase regions as surface perpendicular to the PT plane. This is expected since the projections of the two phase regions on the PT plane are lines. All the two-dimensional diagrams we have discussed so far are merely projections of this three-dimensional surface onto the appropriate planes. A PV diagram is just a projection of the PVT surface on the PV plane, and a TV diagram is nothing more than the bird's eye view of this surface. The PVT surfaces present a great deal of information at once, but in a thermodynamic analysis, it is more convenient to work with two-dimensional diagrams such as the PV and the TV diagrams. Property tables. For most substances, the relationship among thermodynamic properties are too complex to be expressed by simple equations. Therefore, properties are frequently presented in the form of tables. Some thermodynamic properties can be measured easily, but others cannot and are calculated by using the relations between them and measurable properties. The results of these measurements and calculations are presented in tables in a convenient format. For each substance, the thermodynamic properties are listed in more than one table. In fact, a separate table is prepared for each region of interest, such as the superheated vapor, compressed liquid, and saturated regions. But before we get into the discussion of property tables, we define a new property called enthalpy. Enthalpy, a combination property. In the analysis of certain types of processes, particularly in power generation and refrigeration, we frequently encounter the combination of properties U and PV. Here, U is the internal energy, P is the pressure, and V is the volume. For the sake of simplicity and convenience, this combination is defined as a new property called enthalpy and is given by the symbol H and is represented by this equation as H is equal to U plus PV, or capital H is equal to capital U plus PV. Both the total enthalpy H and the specific enthalpy H are simply referred to as enthalpy, since the context clarifies which one is meant. Notice that the equations given above are dimensionally homogeneous. That is, the unit of pressure volume product may differ from the unit of internal energy by only a factor. For example, it can be easily shown that 1 kilopascal into m cube is equal to 1 kilojoule. In some tables encountered in practice, the internal energy U is frequently not listed, but it can always be determined from H is equal to U plus PV. So friends, here we come to the end of our discussion in today's lecture, and therefore we sum up. Thermodynamic property diagrams are diagrams used by scientists and engineers to represent the thermodynamic states of a material and the consequences of manipulating this material. For instance, a temperature entropy diagram may be used to demonstrate the behavior of a fluid as it is changed by a compressor. So that is it for today. In the next lecture, we shall be discussing more about thermodynamics. Thank you very much.